Okay, it says you are recording. Be sure to let everyone know that they are being recorded. Y'all are being recorded. Says you are. Okay, I was going to let it go for just a minute to make sure the recording works because this morning it kicked me out and I didn't realize it until it's too late. So I don't see it turning off. So I'm going to go ahead and share my screen. This one. Can't display content. File might have been deleted. Okay. Let's try a different one. Which I don't understand how that's even possible. Oh, here it is. It's just the wrong one. Presenting. Okay. Still shows that it's recording. All looks good. Okay, so I will start here and just kind of go through. Oh, yes, this works. Okay, so yesterday we kind of went over the beginnings of this electric circuit theory. This is the third entry in your table of contents. First one was nature of matter, second was nature of electricity. Now we're in electric circuit theory. And we talked about the atom and that there's the protons and the neutrons in the nucleus, and then you have electrons floating around it, which you all should have learned in 7th grade. And that the electricity or electronics is all based and it's all based off of the valence electrons or the outermost free electrons of an atom. So then we talked about what a valence electron was, which I just kind of explained. And then looking at this particular element or this atom, you can see that there's, you can't see my pointer. Hold on. Let me turn on my pointer. I figured this out this morning. So I got this laser pointer. So you can see that there's one valence electron, which is floating around, and these are very easy to come off of the atom. And that's what makes electricity work. Okay, so now I can't use the mouse clicker. Okay. And the ones on the inside are too tightly bonded to the atom, so they don't really help with electricity. We talked about what conductors are, which is anything that has 3 or less valence electrons or free electrons. And that makes basically good electricity. A conductor allows electricity to flow through it. And you can see that all 3 of these elements have one valence electron, which is what makes it such a good conductor. We talked about the top 4, gold, silver, and copper being the most common, and then superconductors being something man-made that is better than any natural resource. We talked about what a superconductor does and how they have high temperatures that make them 100 times better than copper. All right, then we talked about what an insulator was, which was 5 or more valence electrons. Those are the things you need to remember. Y'all will have a quiz coming up probably on Monday, just to kind of go over the first 3 sections of those notes. Pause for just a minute. I can't pause, I'm recording, but what's up?
I was stuck in welding.
Yes, you do.
And I have to use the restroom. Can you unlock the staff restroom for me?
I don't know, can I?
Well, no, you have to. I'm not allowed to go to the restroom here.
Am I allowed to?
Yes, you have to. Oh my gosh. It's in my 504.
Okay. Can I just do this?
Not technically.
Oh, okay.
No?
Okay, so I'm gonna put this back up there. You guys can finish this part. Let me get to the point where I need to, and then yes, I'll do that. Okay. Rubber, wood, and pure water are all very good insulators. And you can see that they have more than 5 valence electrons in their outermost ring. Okay. The neon? Neon is supposed to be an insulator, but if you shove enough electricity through it, that's what makes it glow. And so that's why people use neon to make lights. Because if you put enough electricity through them, they glow and it looks pretty. Do what? Yes, kind of. Only a glow stick is a chemical reaction. It's a little different. Okay. Semiconductors, they all have 4 electrons. So 3 or less is a conductor, 4 is a semiconductor, more than 4 is a insulator. Semiconductors can be changed. You can mess with them with their chemical composition and make them change. So you can turn them on, make them an insulator, or turn them off and make them turn them on and make them a conductor, or turn them off and make them an insulator. Okay. Silicone is usually the most widely used one, but there are others on that list. Okay, and then we showed you the periodic table, and where you can see all of the semiconductors here, and then everything to the right of that is going to be your insulators, and everything to the left of that is going to be your conductors. And you should be able to see right here, these are your 3 most used conductors: copper, silver, gold. Okay? Everybody get that? All right. Then we got to load, and what load is, and basically it's anything that requires electricity to run. And that all loads have a value of resistance. I would write that down. Make sure you have that in your notes, because that's important. Talked about a transducer, and that's anything that turns one form of energy into another form of energy. And most loads are going to be your transducers. So in some way or shape or form, they're going to use electricity to create some other form of energy. And then this is the basic circuit. This is where we should be. So you guys need to go ahead and draw a crude drawing of this with the battery and the wires going into the light bulb and then back to the battery. This is called a closed loop circuit. And I'll be right back. Yeah. You should try to keep in order. Skip a few pages before you start putting this in there. You're every page. All right, I'm back. So the main thing that you guys need to get from this is what a closed loop circuit is. Basically, it makes one loop with no opening. And the electrons flow from the negative side to the positive side. And don't forget, you'll have a quiz on Monday, so make sure you're getting all this information. I know. Well, truth is, we're 3 weeks behind. So really, we're just playing catch up right now. And then normally, we're always 3 weeks behind throughout the year, so that really puts us 6 weeks behind where I'd like to be. I'm hoping that this year we will get to the end. I've never made it to the end of the class, so I'm hoping that by this year, this will be our year where we can get to the end and get to do all the robotics portion, and it'll be fun. It's like all the fun part at the very end, but we've never made it there. So.
Why is it like 1, 3, 2? Like, yeah, how pathway in the directions are along this way?
I don't know. I didn't make the PowerPoint. This is not one of my PowerPoints. It is a PowerPoint that was designed, and it actually is really good, but yeah, I can see that being an issue. But I guess it's just numbered that way.
I'm going to do 1, 2, 3.
It doesn't really matter.
Okay.
Like, I'm not even sure why they have numbers there. All right. Does everybody have this? It doesn't have to be it doesn't have to be perfect. Just a simple diagram showing that this is a closed circuit. That's fine. That's better than I would have drawn. Truth is, I would have drawn like an oval with a little light bulb and power supply, and I've been fine. Didn't need to look exactly. Do what? Yeah. You guys are gonna see a lot of crude drawings coming up because there's a lot of schematics we have to draw, and mine are always weird. Huh? Yes. I would write down that this is a closed loop and that electrons flow from negative to positive. I would definitely have that in my notes. There'll be quiz questions too. So, you know what? I don't know if you guys know me very well, but I'm not a really big fan of multiple choice. So I wouldn't count on a multiple choice quiz. I'm not a big fan of them. The issue is that half the time it becomes, instead of a multiple choice, it becomes multiple guess. And you're just trying to take a guess. And the truth is, with a multiple choice anything, you can pretty much narrow down to 2 answers, and then you've got a 50-50 shot of getting it right. At that point, you're guessing. And I would write this is a closed loop, and electrons flow from negative to positive. That's all I would write. Okay. However, I'm not going to wait for him to finish writing because by now y'all should have that. So I'm going to move forward. Okay, 4 parts of a circuit. That's why they numbered it, because on the next one they used it again. 4 parts of a circuit are power source, load, pathway, and control. Those are your 4 parts. We talked about what a control was and how resistance is really your control in your circuit. We talked about that yesterday. Yeah, I would write down the 4 parts, which are power, load, pathway, and control. It's okay. You doesn't have to be in that particular order. And those are just the 4 different parts. But if the pathway is broken from negative to positive, if there's a break somewhere, then electrons cannot flow and no work gets done. Basically what they're saying. If you have a break in the circuit, nothing works. Okay. Yeah. Nothing goes through. And so it's the control right there can be a switch, or it can be a resistor, or pretty much anything that would control how many electrons are actually getting through. Okay. How can I check to see? Okay. Yeah, because Hashir is trying to get in. Okay. And then there's chats. I need to get in. Oh yeah, I'll let you in. Okay. Go. How do I go back? Here. Yeah. Okay. It worked. Okay. Everybody good with this? Okay. 4 parts. If the pathway is broken, no electrons get through. That's all you need to do right now.
Power is broken, no electrons. Like if you have the light is out.
Exactly right. When you flip a switch on, you're basically making the control or the pathway complete. And when you flip it off, you're breaking the pathway. And that's why it doesn't work. Pretty simple. Everybody good? All right, let's move forward. This function of every, this is the function of every switch, basically what I just told you, okay? Opening and closing the circuit is turning it on and off, basically what I just said. Okay, what is voltage? Voltage is named after Alessandro Volta. You'll want to write his name down. Could be. Truth is, I don't remember because I wrote the quiz like 2 or 3 years ago, but it very well could be. This would be something I think I would put on there. And I'll put everything on there so you can write it down. Alessandro Volta invented first practical battery in 1799. And your voltage is your reason for those electrons to move. This is the push, or what's pushing those electrons through the circuit. It's also called potential, which is why that's written there. So another word for voltage is potential. So electrons don't want to move from one atom to another. They need some sort of push. So any kind of force, chemical, magnetic, mechanical, or whatever, that gives them that push or that reason to move is called voltage. Okay, I can't honestly read what it says right there.
I think somebody was lobby.
Oh, are they?
I heard the sound.
Yeah, sure was. Yeah, somebody else will have to like show me that. So, or let me know, because I don't ever hear that. Yep. Okay. So basically, what they're saying here is just because you're trying to push something doesn't necessarily mean it's going to be able to pass. So when I was talking about neon and how you have to have more voltage, that means you have to have a bigger push for those electrons to jump through it. The same way we were talking about lightning and how it needs a massive push in order to get it to jump from the clouds to the ground. You need to have more voltage or more push to get those electrons to jump.
Right.
What's that?
How do you paraphrase that?
How would you paraphrase that?
Yeah.
I would say, first of all, voltage can also be called potential, because you need to know that. And then I would say any push or any force that pushes electrons to move from one atom to another is voltage. That's kind of how I would say it. Any push or any force that pushes electrons to move from one atom to another is voltage. That's how I would put that.
You learn to move
from one atom to another.
One atom to another.
Yeah. Basically right here, starting at this point right there to this point here, that second sentence. Yeah. That's the main definition. Then Alessandro Volta, 1799. I would know those numbers. That name. Yep, the date and the person.
Isn't it like a car? Like the actual car battery?
It's very similar to that. That's a battery, and batteries are chemical reactions. And now what you see in cars today kind of looks very similar to that, only way more advanced. So it's the same kind of idea, probably different types of chemicals, probably hopefully something a little more safer that they're putting in cars. But if you ever take apart, like if you ever go look up like a Nissan Versa, the hybrid ones or the electric ones, like you can buy their battery packs online, and all they are little AA batteries that are like mounted together with a bunch of others. Yeah, but they're a specific type of battery. It's the rechargeable type of battery, so it has a specific type of chemical. It might be. Oh, next one is resistance. You're so smart.
I know, right?
Okay, so it's not named after anyone. It's named after the word resist because it is resisting the push of the electrons. So that's why it's called resistance. It is basically resisting or pushing back, I guess, keeping that push from happening as easily as they'd like it to. But the opposition of movement is kind of what they're pushing for here. Measured in ohms. And this particular man is Greg. Well, we've talked about this. It looks like George, but we decided that it might not be George because there's no E at the end. So it might be Georg or something like that. Simon Ohm, he's the one that created the Ohm's law. And Ohm's law is the basics of all electronics. So this is why it's measured in ohms. Huh? That's his last name. Oh. That's his last name. An ohm is the measurement of resistance.
Oh, his name is George. Oh.
Yeah. Georg, or George. You can just say George. We're just going to go with George. George Simon Ohm. Came up with the Ohm's law, and that's why we measure resistance with ohms.
So basically,
resistance is the opposition to the movement of the electron, or what's resisting the movement. And George Simon Ohm is the discoverer of the Ohm's law, and that's why we named resistance, or that's why we measure resistance in ohm. George Simon Ohm. At the very bottom.
I'm gonna ask Google Translate how to say it.
So I put the this means the unit of electron is described by the
That symbol on the screen right there, that is the omega symbol right here. Yep. It's also the symbol we use for ohms. So whenever we're going through that and showing measurements, that's going to be your symbol. And we will, Georg? Yeah, that's what I was wondering. Georg. Instead of George, it's Georg. All right. So hopefully you guys got all that. Move forward. Amperage was named after Andre Marie Ampere. And he was one that basically connected electricity to magnetism. So amperage is how many electrons pass through a certain point at a certain time, or during a certain time. So this is an amount per time. Okay, so amperage is the dangerous part. This is the part that can kill you. So you have to be careful with how much amperage you have in a circuit. Huh? AMP? Yeah. Just remember his name is Ampere, and the name of the amp stands for amperage.
Oh, wow.
Yeah. This is the scary stuff. This is the stuff you got to be careful of. It only takes 0.5 of an amp to actually kill a person, so we decrease or keep our amperage very low so that isn't ever going to be an issue in class. But and then of course they're going to show you a guitar amp, which has nothing to do really with amperage. Just called that because it amplifies the sound, which is a little different than amperage. It's called an amp, but it's not in the same way.
So,
So you don't need to worry about that. That's this particular person that created the PowerPoint made it into a joke, and it's supposed to be funny, and we're gonna move forward.
okay.
Yes. Okay.
We're not gonna do that.
So no, this is just an example of to kind of help you understand amperage. Okay. So I'll read this to you guys so that you can understand what's going on. Coulson and Houston's discipline plan. If you mess up in class, they take you to a beach and tie you to a post, then call the Weather Bureau and order a tsunami to head straight towards you or toward where you're standing. The one rule, in order to get back into class, you have to be able to withstand being hit with 10 billion gallons of water. So the question is, how can you follow the rules and still survive being hit by 10 billion gallons of water? Right. But how are you going to withstand 10 billions of gallons of water being poured on you?
Oh, like poured or the?
Like hitting you. Yeah, you're going to get 10 billion gallons of water hitting you.
I don't know.
You get the full, the pouring zone.
Right, but that's, I mean, we're talking about lots and lots and lots of water. No, it has to hit you. So how do you survive that much water hitting you?
When you're tired.
Hold your breath.
That's a good try, Ross. No, how can you withstand?
You swim.
Okay, but it's all gonna hit you. So how do you keep it from? You're tied to a post. You're not gonna be able to surf.
How do you order the tsunami though?
We have powers. It's cool. Okay, so
I don't know, maybe you just can't.
you can. There's a way. However, okay, so normally I let you guys kind of sit here and try to figure it out, but I'm just going to kind of move on and explain it to you because we have less time and we're farther behind. Okay,
Boy, I could look at the answer the whole time. I think.
you could have right there. Okay, so the answer basically is that you be hit by very small amounts at a time. So you can still be hit by 10 billion gallons of water. It just may be over a very long period of time in very small amounts at a time. So basically, like you're getting hit by, like what they're saying, one glass at a time. Eventually, you'll be hit by 10 billion gallons of water. It'll take a long time to happen, but you'll survive it. So you just be wet. And then you'd be able to go back to class. Of course, who knows how long it would take to get 10 billion gallons of water hitting you over and over again, and if it was just a glass.
I think I'm here had a question.
Oh, did he?
I think he put the thing down.
Okay. I don't see anything on my screen, so.
Put it down.
Okay. This is an example of the difference between voltage and amperage. 10,000 volts is only dangerous because like all that water, it has the potential to do some serious damage, but only if it's all unleashed at one time. 10,000 volts won't kill you if you're getting shocked by 10,000 volts over a long period of time. So it's not hitting you at 10,000 all the time, hitting you 10 volts each time, and you won't really feel it. No, it's just an example. It's just kind of trying to show you the difference between amperage and voltage. So if your high voltage has low amperage, it won't be an issue. You'll be safe. It's whenever all of that voltage hits you at one time, like a lightning bolt, that it would become an issue.
I got hit by a lightning bolt.
Oh, yeah?
Yeah.
Mm-hmm. Okay, and so that's when you have a problem. So it's not necessarily how much voltage you have in something that makes it dangerous. It's how much amperage you have and how much of that voltage is going to hit you at one time. Okay, that's where you have to be careful. So amount per time is what's dangerous, or amperage. Okay, current flow. We just wrote this down in our notebook, so it's not necessary for you to write it down again. But the current for electrons flow from the negative terminal to the positive terminal through the circuit. This is a negative. This is called a negative current flow because it normally, when electrons are negatively charged, and that's why it does that. And we talked about the fact that you have a negative charge element or atom, and it is going to go towards the opposition or the positive. So it's going to flow towards the positive. If they were the same negatively charged atom, it would repel from another negatively charged atom. But that's why it goes from negative to positive. Okay, so write down electrons are negatively charged. Oh, just write down that that's called negative current flow. Yeah. Whenever your electrons are going from the negative side to the positive side, that's called a negative current flow. You can manipulate a circuit to do the opposite, but in electronics we work with one specific way. So the negative electrons flowing from negative to positive is called negative current flow. All right. Everybody good with that? Okay, Ohm's law, relationship between voltage, resistance, and amperage. Okay, so we could go through this long definition, and like this is kind of what they're showing. This is the actual definition. We don't need to write all that down. It's too hard. The words are too complicated to really make sense of all of that stuff. So we're going to simplify it. And that's basically what this PowerPoint does. Helps simplify. So Ohm's law, make sure you get the relationship between voltage, resistance, and amperage. That's the definition you need to have down for Ohm's law.
The relationship between voltage and amperage.
Yep.
Ohm's law.
The PowerPoint actually was taught by my ex-teacher. So in that example, they talked about Woolison in Houston. Woolison was my teacher in high school.
It's like, if you just like one thing in this class, you're on at 8, like you're behind.
Oh yeah.
Like the class for the math I can.
Yeah, you're gonna miss some. But the PowerPoint's up there, so you can always go back, and then I'll be putting this video up, so you can always come back and watch it. Okay, so that's all we needed, the relationship between voltage, resistance, and amperage. So let's use an analogy. This analogy, okay, let me just get you ready for it. It's a little cheesy, okay? It's a little rudimentary, very simplified, elementary maybe, okay? However, for whatever reason, having taught this for a few years, I taught it without doing this analogy, and then I've taught it with using this analogy. For whatever reason, it works. People understand better after we look at this analogy. For some reason, that's just the way it is. Okay, so you ready? It's a little cheesy. All right. Mice.
Okay.
Okay. Mice are going to represent our electrons.
Okay.
All right.
No.
No, just this isn't something you need to write down in your notebook. It's just something so that you understand. Like I told you before, we're talking about wanting you to understand the concepts, not write everything down. I want you to understand how this works. Okay, so electrons are mice. Okay, voltage is the reason those mice want to move, right? They want to get to the cheese. So it's their reason for moving from where they're sitting right now over to where the cheese is. Kind of. It is cheese, right? Okay. So the electrons want to move to the cheese because that's their reason, right? They like cheese. All right. So we got a problem though. All right. There's cats. And they are the resistance. They're the what's opposing the movement of those mice. It's keeping the mice from being able to get to the cheese. Okay, does everybody get that? So cats are our resistance. All right, so we got electrons over here that are trying to get to voltage over here, but we got cats or resistance in the middle, keeping them from being able to get there. All right, this is our analogy. Maybe, here we go. All right, then there's a line drawn, okay, and this is our amperage line, okay? Amperage is the number of mice that get past those cats to get to the cheese per unit of time. So per second, how many mice get past that line? That's our amperage. Does that make sense? Okay. So y'all ready? Now we're going to explain how Ohm's law and how electricity works. All right. Two things that can be done in order to increase the number of mice getting past that line. What are the two things that can be done? Okay, removing the resistance or decreasing the amount of cats that are there, right? Okay, what's the other thing? Okay, we're talking, it's about the cheese. What do we need to do to the cheese? What do we need? What would make their incentive to get over there more? More cheese, right? Getting more cheese or more voltage will make those mice want to get across that line fast. Does that make sense? So there's two different ways that we can increase amperage. Okay, so decreasing resistance, reducing number of cats, or decreasing the resistance will make our amperage go up. Or increasing the amount of cheese. Both of those two ways will make our amperage go up or make the number of mice get across that line faster. Does that make sense to y'all? Yeah. Okay. This is how electronics and electricity works. So you can decrease the resistance to get more amperage, or you can increase the voltage. Does that make sense? Hopefully everybody gets that. But that's how you would increase amperage. And in some cases you want to increase amperage, some cases you want to decrease. So if you wanted to decrease, you just do the exact opposite. You would decrease the cheese or increase the resistance. Does that make sense? Okay. So to decrease amperage, same idea. We are going to increase the number of cats. Or well, some of them, they're just fancy cats. You got some fancy mustaches. Oh yeah. So that will decrease the amount of amperage going through. Or we can get rid of some of the cheese, and there's only a little bit of cheese for those mice to get across, and that decreases their incentive for wanting to go. Okay? So do y'all understand that? Online, everybody online, anybody online not understand that? This is one of the concepts that we want to get through. Does anybody have any questions about how that works?
So basically, electronics, and the voltage, it'll get over there.
If you increase the electrons in the, yeah, sure.
Okay, so if you increase the resistance, yeah. So,
That decreases how many get through. Yeah.
so if you decrease the voltage, but if you have those many mice and like one cheese, what would happen? Like one voltage. Like if you have those many electrons, like one voltage.
Well, the amperage is going to drop because you don't have as much cheese there.
Okay.
Yeah. Okay. This is just something that you want to write down. You don't have to like draw all nice and neat, but basically what Ohm's law is proving is that when you increase amperage, you are decreasing, or when you increase resistance, you're decreasing amperage. So that's what you want to write down. And that's called being inversely proportional. So if one goes up, the other goes down. Oh yeah, I'm teaching them Ohm's law. I know. We're going to see if this actually this online thing actually works and how many get it. Because I'm doing a live chat too, so we'll see. Okay, so if you increase resistance, that decreases amperage, which makes them inversely proportional. If you increase voltage, what happens to amperage?
It goes up.
Goes up, which makes them directly proportional.
Inversal, what I said.
Inversely proportional. One goes up, the other goes down. With voltage, if voltage goes up, amperage goes up. Hopefully, I'm hoping, crossing my fingers, that this concept and this way of teaching still gets across to those kids at home. And if we all understand it, then it's been a successful trial with this. So this tutorial time would be hard. All right, is everybody good with that?
Yeah.
Okay, so we're not going to do this. We're going to go to this, Ohm's law. These are the equations for Ohm's law. They show you that E is voltage, I is amperage, R is resistance, and then these are your different equations. You could basically remember all three of those equations, but all three of those equations are really the same thing if you've been through algebra.
So
You can remember this particular symbol right here is Ohm's law. Okay, they use E here. We will use V for the most part, but we'll talk about why they're using E for voltage, I for amperage, and R for resistance. And yes, I would definitely write this. If you understand this symbol, you've had science classes that use that kind of symbol, then I would definitely write that down. I'd write them all down, honestly, but for sure this one, because we're going to talk about how that works. But this is Ohm's law. Voltage is equal to amperage times resistance. And then all of these other equations are, this right here is the main one. V equals I times R. Okay. The rest of these, R equals voltage over amperage, is just solving for R here off this equation. So if you divided I on both sides, you'd end up with E over I, which is what you get here. Amperage, voltage equals amperage times resistance.
So for E, amperage and resistance.
Yeah, so voltage E is equal to amperage times resistance. That's the main, that's Ohm's law.
So resistance equals voltage divided by amperage?
Yep.
Okay. Make sure that one.
Yeah. But again, like I said, those other two equations, they're just solving this equation. They're resolving this equation for a different variable. So they're solving for R here. If you solve for R, y'all have had algebra, right? Okay. So if this is the only equation you have, you solve for R, you're going to divide I on both sides, right? That's how algebra works.
Okay, so if you want to find an R, you would use E divided by 1.
You have this, and you want to solve for R, you divide by I on both sides. These cancel out, and you end up with R.
Or could you just do the I divided by E?
The I divided by E.
So you're dividing by both sides of each of our I.
Like,
Right. This is just basic algebra. So we're just solving for R off that first equation.
I was saying, if you just want to find R, could you just do this one?
Yeah.
Okay.
But what I'm saying is like this equation is just this equation rewritten to solve for R.
Okay.
This equation is just this equation just solved for I.
What if you just have like a voltage?
If you just had the voltage?
Yeah.
Well, that's what we're going to talk about right now. We're going to get there. I'm going to show you how this all works and why you would want to know all three of those equations. Okay, the truth is you don't really need to know all three of those equations. What the best thing to do is to know this right here, because that right there is going to help us know all of it. So, and I'm pretty sure they're going to explain it to you. Yeah. Okay, so this symbol is basically your entire Ohm's law. If you were solving for voltage, you would cover up the E, and I have no way of like putting a hand over the E, but if you imagine not seeing what the E looks like, or not seeing the E there, you would not have divided by. This is a multiplier. Right. You cover up the one that you're looking for, and it gives you your equation. So if you cover up the E, you'll see that I times R. If you're looking to solve for amperage, and you cover up the I, you have E over R, which is voltage over resistance. And that's how you would be able to solve for amperage. If you were trying to solve for R, you would have voltage over amperage. And that's why this symbol is easier to remember than those three equations, because you can find your equation just by covering up the letter that you're trying to solve for. Now, I don't know if they do that in here or not. It'd be nice if they did. Huh? No. Don't forget it. Okay, so like I said, this PowerPoint, there's a couple of things they're trying to make it seem funny. Some of it I would be like, well, whatever. But yeah. Yes. No, this is, but the people that wrote the PowerPoint are like the creators of PLTW. Like they wrote the curriculum and all that, but this is separate from PLTW. They wrote this. Like Houston was the one that trained me to teach this class. Yeah. When we were talking about the tsunami equation, it said Coulson and Houston. Well, Coulson was my teacher in high school, and Houston was the trainer. Yeah. Okay. So now we're going to talk about why we're using the letters that we're using in Ohm's law. Okay, we get the R is for resistance because that makes sense. R, resistance, they both start with the same one. But why are we using I and why are we using E instead of V for voltage and A for amperage? And this is why. Because before volts were named by Volta, they were called electromotive force. You want to write that down. That another word for voltage is electromotive force. Okay? That's something you want to write down. We also wrote down that voltage is also called potential, so don't forget that. Voltage is also called electromotive force. That's something else you don't want to forget. Okay, that's why we use the letter E for it. Later, when we actually start doing this, we're probably going to go back to the letter V. But at the beginning, they want us to use E. Okay. So this is the force that moves electricity, which we've already talked about. That's what voltage is. That's what pushes the electrons. So basically, they say that it's stuck. I'll tell you, when I learned it, we learned it with a V. So I'll probably teach it to you with a V. That's V for voltage. It just makes sense. That's kind of how I learned it. So
we just put both.
Yep, that's all you really need on that one. Voltage is also called electromotive force.
All right. But what about the I?
Exactly. Thanks, Cameron. What about the I? So before amperage was named by Ampere, it was just called intensity, which is how intense the voltage was, how much voltage per second you were getting. Okay, so that's why we use I for amperage. And we do stay with the I for amperage throughout. So it just means intensity. It's the intensity, how strong it is. Huh? I would, so that you know why we use the letter I for amperage. Because we will do that.
For amperage, like in a phasor, or like a
Yes, low amperage, high voltage in a phasor.
so we can say how many phasors do you have to take?
Depends on the person. We're not going to test the theory in the class. Sorry. It's not really something we're going to make. We don't really make tasers, but
I wish.
you know, when you're an adult and you want to try that, that's on you guys. But I don't really like getting shocked. I've been shocked numerous times. Not really my thing. Like it happens, but I don't sit there and go, oh yeah, I'm gonna try that again. No, I don't really like it. So.
I got shocked by fixing a light switch.
Yeah.
We were putting in a new plate or new switch because it was broken. I got shocked because I put my hand like that felt weird.
Yeah, it feels weird. Those don't hurt. Those don't really like. It's not really a hurt. It's more of a that was weird. Yeah.
Like one of those shock.
Yeah, like the gum thing. Yeah.
Okay.
It doesn't really hurt. It's just surprising and it's weird. Yeah. But the more amperage you get, the more it hurts. So.
I got used to it.
Okay, so that's why we call it I, or that's why we use I for amperage. Okay, so there's only 3 different circuits that we actually have to learn in this class. So we're going to talk about that in the fundamentals here later, but the 3, I think we're going to go over that. The 3 circuits, we're going to write down what they are. Okay, so there's 3 different circuits that you need to know. The first one is called a series circuit. And a series circuit only has, right, it only has one pathway. So it's going to go from one side of the terminal to the other side of the terminal, and it has to pass through every resistance or load that is on that wire. Okay, so it can't skip anything. Do what? I would draw a picture like that.
So
To kind of show you that it's a closed loop, single pathway.
So this is one pathway, negative positive.
Right. Okay. If one light bulb burns out, the rest will not work. So one of the things that I was trying to explain, like, I don't know if you guys put lights up in the holidays, but if you ever had a light strand, you can tell the difference between the light type or the types of lights you get. If you buy the cheaper ones, they're made as a series circuit. One light bulb goes out, they all go out, and then you have to figure out which light bulb is out, and that most people just throw them away at that point because you can't really. It takes a long time to figure out which light bulb burned out. And that would be a series circuit. It's the simplest way to make a circuit.
If one burns out, they all
go out. If one goes out, they all go out.
Well, you can probably tell by the color of it.
I have quite a few strands of holiday lights like that, and I have a very, like, once it burns out, it's kind of like, I can go through and replace the bulbs and figure out which bulb is burned out. And they also make testers, so you can test them. But it takes a long time when you got 150 light bulbs on one thing, and then you're like, well, it only costs $3 to buy a new set of lights, so most of the time to buy a new set. Especially considering $3 doesn't buy you much anymore. And that's a series circuit, though. Everybody got that one? All right. The next one is a parallel circuit. This one has more pathways that'll lead from the negative to the positive. So it can go on the first pathway where it would go up here and come around, or it could go on the second pathway, or it could go on the third pathway. These are a little better. This is a better circuit. If, what's that?
Only one light bulb goes out, one light.
Right, if one light bulb goes out, it's only affecting that part of the circuit, so the rest of them will stay lit. Which is this is a better circuit for things like that.
What's the extra bulb for?
Yep. So on a parallel circuit, there's multiple pathways. So if one burns out, it only affects that particular pathway. It doesn't affect the rest of the circuit.
Or easier.
This is a higher quality. These are the $5 light set that you buy at the Walmart. So it's a little bit better. We're almost done. All right. It's a parallel circuit. Yep. All right. Series parallel is the third one, and this is where we're going to stop today. But a series and parallel has both series and parallel sections. So if you look at this first part, you can see that this part right here, these two light bulbs is on this path are in series together. What you'll notice is that this light bulb here is in the series, because if this one were to go out, it's going to take out all of the whole circuit, right? If this one goes out, it's just on this one pathway. So this one and all the other three will stay lit. If this one goes out, it only affects itself. But if this one goes out, it affects the one that's in series with it. So it'll be both of these two. So that's why this is a combination where you have both series and parallel circuits together. So it just depends on which light bulb goes out that would affect the rest of the lights. I don't know. Okay, and that's as far as we're going to go today. So, but those are your three types of circuits: series, parallel, and series parallel. We only have one more slide? Okay, we'll do the last slide. We only have one more. I didn't know how many we had left. Okay, so this is it, analog versus digital. What we're learning right now is analog circuits. So in an analog circuit, you have a variable signal continuous in both time and amplitude. This is going to be a little bit above what we've gone through so far. But basically, you have a signal or electrons that are flowing all the time, so that it continues over time doing that specific circuit. It's always going to be that same output over time. Okay. In a digital, we are using what they call discrete values. So some of these are numbers and non-numeric symbols, such as letters. So we'll use some variables. This is where our Algebra 2 comes in with this class. And most of y'all have not taken Algebra 2, and that's okay, because by the time we get to the Algebra 2 portion, I usually am able to explain it without you actually having had Algebra 2 in it. So it's okay. But this one has a different output based on how much time you've used that circuit. So no, not really. We're going to go through it later. But at the beginning, the first 9 weeks, we only deal with analog, just so that you have one definitive answer, no matter how long it's been going. Okay. Second 9 weeks, we start dealing with digital, and that's where your answers will change depending on how long that circuit's being run. Okay, and that's the difference between analog and digital circuitry. It's going to be fun.
You always say that.
And it's always fun.
You always say that. Like, Ever since last year. It's always fun.
It's gonna be fun. Yes, so hopefully everybody got all that. If you have any questions, post them up in the comments and hit subscribe and like on my YouTube channel. And that's about it. I'm gonna stop sharing. And I'm gonna stop recording.
Bro, you should have Mr. Beast shout you out. Yeah, he'll give you 1 million subs.
Cool. I don't know who that is.